Hi, this video is going to take a look at normal distributions and the standard distribution. And normal distributions are appropriate when we're using continuous random variables. We have different techniques if we have binomial or other discrete types of distributions, which we've dealt with in other presentations. And continuous simply means there's an infinite number of possible values, so fractions between whole numbers. And so this is what we're looking at. The time spent studying, for instance, can be any number between 0 and 24, including fractions of hours into minutes and so on. So the probability distribution of a continuous random variable is called the continuous probability distribution. There's some properties of normal distributions that are useful for a number of reasons. The most important probability distribution is the normal distribution because so much is based on it. It's a continuous probability distribution for a random variable x, and the graph of it is called the normal curve and has this familiar bell-shaped curve to it. And the normal distribution has the following properties. The mean, median, and mode are all equal. It's bell-shaped and symmetric. That's the other thing. It's unlike, say, the chi-square distribution, which is not symmetrical. We have the total area under the curve equal to 1. So similar to the idea of discrete distributions, which also total to 1. This is the case with the normal distribution. And 4, the normal curve approaches but never touches the x-axis. So it's a limit. It just approaches a limit, never crosses it. And 5, between mu minus sigma and mu plus sigma in the center of the curve, the graph curves downward, so the graph curves upward to the left of n minus sigma and to the right of n plus sigma. And the points at which the curve change from curving upward to curving downward are called inflection points. So as we see, total area of 1, as we mentioned, and of course the inflection points represented by the standard deviation from the mean, mu, and x. If x is a continuous random variable having normal distribution, mean mu, and standard deviation sigma, you can graph the normal curve with this equation, y equal to 1 over the standard deviation times the square root of 2 times pi, and this term by e raised to the minus x minus mu squared divided by 2 times the variance. And where e is the base of the natural log and pi, you're familiar with pi also. A normal distribution, and we haven't mentioned the standard normal yet, this is just a normal distribution, can have any mean and any positive standard deviation. The standard deviation just describes the spread of the data. How spread out is it? We could talk about how flat or how peaked it is, how skewed it might be if it's not symmetrical, but if it's normal, it is symmetrical. So here's an example where the mean is 3.5, here it's 6, and the standard deviation here is 1.9, over here 1.3. So you can get a lot of different numbers plugged in there for the normal distribution. We can also compare distributions where maybe we have two side by side like A and B here. And we can think about the question, which curve has a greater mean? And which curve has the greater standard deviation? So which one is more spread out? Which one has the highest middle? And the line of symmetry of curve A occurs at 5, which is the mean, median, and mode in a symmetrical distribution. The line of symmetry for B is at 9. B has the greater mean. Curve B is also more spread out, as you can tell by how flat it is. And so B has a greater standard deviation. In this example, we're looking at the heights of magnolia bushes, and those are all laid out here in a symmetrical fashion, and the middle will be the mean, median, and mode of the magnolia bush heights. And then, of course, you're going to have some that are extremely tall, but the taller we get, the less frequently we see that. And we're going to have some that are extremely short, and the shorter we get, the less we're going to see of those. And so that's how we interpret the normal distribution. The inflection points, now one standard deviation away from the mean, in this case, are 0.7, the mean is 8. And now we come to something called the standard normal distribution, which is a particular kind of normal distribution with these characteristics: a mean of 0 and a standard deviation of 1. And the nice thing about this is any value can be transformed into a z-score by using the formula of z is equal to the value minus the mean. So we know that's the deviation divided by the standard deviation. So we're just going to be standardizing the deviation. And that will give us our z-scores. And if we transform all of the values of a particular variable in this way, then we will have created the z-scores for everything. Right? The result will be the standard normal distribution. The area that falls in the interval under the non-standard normal curve is the same as the area under the normal curve. So after the formula is used to transform an x value into a z-score, the standard normal table found in on the z-score table is used to find the cumulative area under the curve. And the standard normal distribution has the following properties. Cumulative area close to 0 for z-scores, close to z equals minus 3.49. And remember, the cumulative area is anything that follows along as we move from left to right. So below negative 3.49 is close to 0. Remember, this line never actually crosses 0. It just gets infinitely smaller. 2, the cumulative area increases as the z-score increases. Right? So as we go from left to right, the z-score is increasing. And as we get to 3.49, we're close to 1. But again, it's a limit, so we never cross the line. So the cumulative area for z equals 0 is 0.5, which is the middle. So that's what we're looking at there. And the cumulative area is close to 1 over here. We can also use a standard normal table to figure out a cumulative area. So if we know a z-score is 2.71, then we can use this table. There's 2.7 and there's 0.01, and that tells us the cumulative area that is covered by that score. Now it's not quite 1. Again, we said 3.49 is where we get to really close to 1. And we know negative numbers are going to be smaller, so negative 0.25, 0.4013 is the cumulative area. So if we want to find the area under the standard normal curve that corresponds to a particular z-score, we have to start by sketching the standard normal curve and then shading in the appropriate area that corresponds to that value. So if the value is 1.23 here, then it's everything over to the left, and that's going to give us what we need. If we want to calculate anything to the right of a value of a z-score, then we start with the cumulative area, so we still need to figure out how much is covered here, 0.8907 in this case. Then if we're looking for the remaining area, we know that the total curve is 1, so if we subtract this number from 1, we're going to get what's left, and that's 0.1093. And beyond looking left and right, we can also look between two values. And using the same kind of logic, we can first calculate the cumulative score of the smaller value, then the cumulative area of the larger value, and then subtract the smaller value from the larger value, giving us the remainder, which is right there, shaded in black here. So here's another example where we're going to find the areas under the curve. For a z-score of minus 2.33, the area to the left, if you look that up on the standard normal table, should tell you 0.0099. And if we want to know the area to the right of the z-score of 0.94, we start by learning what's to the left and subtracting it from 1. And you should find 0.1736 if that's the case. Or here we're going to find between two areas minus 1.98 and 1.07. So we subtract the smaller area from the total area of the cumulative area for the larger value. And that should give us 0.8338 in this case.